Week 12 Capstone Project, Comprehensive Data Mining Case Study. Welcome to your final project. In this lesson, you will combine everything you have learned to analyze and model real datasets. We will work with data about telecom customer churn, credit card fraud, and mall customers. Let us dive in and put your data mining skills to the test. Running the cell now. Let us keep our notebook clean by hiding any warning messages. We import the warnings library. The next line tells Python to hide any warning messages. This keeps the notebook output clean. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. This code sets a fixed random seed and suppresses warnings to ensure clean, reproducible results throughout your capstone analyses. While there's no visible output here, this setup is crucial for consistent data sampling, modeling, and interpretation across all projects in this lesson. Notice how it prepares your environment for reliable and focused data mining work. Try running this cell before any code in your own projects. Part 1. Data Setup. For our capstone, we will use the Telecom Customer Churn dataset. This data includes information about customers, their services, and whether they left, also called churned. Churn analysis is important for businesses to understand why customers leave. Running the cell now. Now, let us load the Telecom Customer Churn data. This comment marks the start of data setup using the Telecom Customer Churn dataset. We import the pandas library, which is used for data manipulation and analysis. We define a URL string pointing to the online CSV dataset file. We load the dataset from the URL into a pandas data frame named df. We print the shape of the data frame to see the number of rows and columns. We print the first 3 rows of the data frame to preview the data samples. Running the cell now. The dataset contains 7,043 customer records and 21 columns, including demographic info, service details, and churn status. Notice the variety of features like tenure, payment method, and monthly charges, which will help us analyze patterns related to customer churn. This setup confirms we've successfully loaded the full dataset to begin our exploration. Practice, try printing df.info to see more about the data types. Checking for missing values helps us prepare the data for modeling. This code counts any missing values in each column. We sort them so the columns with the most missing values come first. This helps us see if we need to clean any columns before we analyze further. Running the cell now. This output shows that there are no missing values in the top 8 columns of our dataset, which is crucial for reliable analysis. Noticing a count of 0 missing entries means we can proceed confidently with data exploration and modeling without initial cleaning for these features. This step confirms the dataset's completeness, aligning with our intent to start with a clean, robust base for churn prediction. If you find columns with many missing values, think about how you would handle them. One way to fix missing data is to simply remove rows with missing values. Here, we use the dropner method. This removes all rows with any missing values. We print the new shape to confirm how many rows remain. After this step, all rows should be complete. Running the cell now. After removing all rows with missing values, our dataset now has 7,043 rows and 21 columns. This step ensures the data is clean and complete, which is crucial before we begin analyzing customer churn patterns accurately. Notice how dropping missing data can slightly reduce the dataset size but improves the quality for reliable modeling. Sometimes, it is better to fill missing values. For now, we are just dropping incomplete rows. Part 2. Data Preprocessing. Let us convert text columns to numbers. Machine learning models in Python need free of text values. We will change categories into numerical codes. Running the cell now. Let us convert all string columns to numbers. We loop over every column that contains words or text. We convert each text column into a category type and then change these categories into integer codes. After this step, every value is a number. This will help with machine learning models. We print the first 3 rows to see that the columns are now numeric. Running the cell now. Here we see the output after converting all text-based columns into numerical codes, which is essential because machine learning algorithms require numeric input. Notice how categorical features like gender and payment method are now represented as integers, while numeric columns remain unchanged. This transformation allows us to seamlessly use these variables in modeling without errors. Try running df.dtypes to check that all columns are now numbers. Part 3, Exploratory Data Analysis, also called EDA. Let us get to know our data by looking at descriptive statistics and class balance. Exploring data helps us spot problems and interesting patterns. Running the cell now. Summary statistics help us spot outliers and get a feel for typical values in each column. This code prints a basic summary of all number columns. It shows things like the average, standard deviation, and the smallest and largest values. We use .t to show the summary sideways for easier reading. Running the cell now. This summary statistics table gives us a quick snapshot of our dataset's key numerical columns. Notice the consistent row count of 7,043, confirming no missing values here, while the mean and spread values help us understand customer demographics and service usage patterns. This foundational step in EDA highlights important distributions and potential imbalances to guide deeper analysis. Practice: try looking for columns with strange or unexpected values. We want to see how many customers stayed versus how many left. This line counts how many rows are in each class for the churn label. Class balance matters because models can struggle if one outcome is much rarer than the other. Running the cell now. This output shows the class distribution of the churn column, revealing that there are significantly more non-churn cases, 5174, than churn cases, 1869. Noticing this imbalance is key in EDA because it informs us about the dataset skew, which can impact model performance and may require techniques like resampling or adjusted evaluation metrics. If the classes are very uneven, try thinking about reasons why. Part 4: the Association Rule Mining, our mini project. Now we will use market basket analysis to discover products that are often bought together. Let us use the Groceries dataset for this step. Running the cell now. Let us grab the Groceries dataset for association rules. This section is for setting up the data using the Groceries dataset. We import the Pandas library for data handling. We import KaggleHub to download datasets and OS to interact with the operating system. We download the Groceries dataset using KaggleHub and get the local path where it's stored. We list all files in the downloaded dataset directory. We find the first CSV file in the directory, assuming it contains the dataset. We read the CSV file into a Pandas data frame named df_groceries. We print the dimensions of the data frame to understand how many rows and columns it has. We display the first 3 rows of the data frame to preview the data. Running the cell now. The dataset contains 38,765 rows and 3 columns, showing it records individual grocery transactions with member ID, date, and item bought. Notice the key columns, member_number and item description, which will help us identify which products are frequently purchased together in the association rule mining step. This initial exploration confirms the data structure is ready for market basket analysis. Try using df_groceries.info to learn more about the data. For market basket analysis, we want each customer's basket as a list of items. We group the items by each customer's member number. For every customer, we collect their items into a list, so we have one list per person. We print out the first 2 baskets to check our data. Running the cell now. The output shows 2 sample baskets, with each list representing items purchased by a single customer. Notice some items appear multiple times, reflecting quantities, which is important for capturing realistic purchase patterns. This format prepares the data for association rule mining by structuring transactions as lists of items per shopper. Think about how these baskets are like real shopping carts in a store. Let us discover which items in baskets are related. This script uses the Melkstend library to perform simple association rule mining. We import the transaction encoder to convert transaction data into a format suitable for analysis. We import a priori to find frequent item sets and association underscore rules to generate association rules from those item sets. We prepare the baskets by encoding them into a one-hot encoded format required by the a priori algorithm. Initialize the transaction encoder object. Fit the encoder on the transaction data and transform it into a Boolean array. Create a data frame with the encoded data, where each column represents an item. Use the a priori algorithm to find item sets that occur in at least 4% of transactions. Generate association rules from the frequent item sets, filtering those with a lift greater than 1.2. Print the first few rules showing the antecedents, consequence, and metrics to understand the relationships. Running the cell now. This output shows the top association rules discovered from the Groceries dataset, listing product pairs like butter and other vegetables with their support, confidence, and lift values. Notice the shape. Each row is a rule connecting antecedent items to consequence, highlighting which products are frequently bought together and how strong those associations are. This directly illustrates how a priori helps uncover meaningful product relationships for market basket analysis. Which rules seem useful to a store manager? Let us keep going. Part 5: Classification Modeling. It is time to use a machine learning model to predict if a customer will churn. We will use the random forest classifier for this task. Running the cell now. Let us separate our target from the rest of the data and split for training and testing. We add a comment to explain that we will split data into features and labels and create trained test sets. We import train_test_split from scikit-learn. X means our features, which are columns used for prediction. Y means our label, which is churn, the thing we want to predict. We split our data into training and test parts. The training part is for learning. The test part lets us check how well our model works on new data. We print their shapes to confirm our splits. Running the cell now. This output shows the shapes of our training and testing datasets after splitting, with 5,634 samples and 20 features for training, and 1,409 samples and 20 features for testing. Notice that the test size was set to 20%, ensuring a solid portion of data is reserved to evaluate model performance later. This split is crucial to build a reliable random forest classifier without overfitting. Practice. Think about why we need to test on data that was not used for training. Now, let us train a random forest, a popular classifier. We start by indicating that we are training a random forest classifier. We import the random forest classifier from scikit-learn. We create a classifier with 100 trees and set the random state for reproducibility. We fit, or train, the classifier on our training features and labels. A message prints when the model is trained. Running the cell now. The output, training done, confirms that our random forest model has successfully learned from the training data. This step is crucial as it means the classifier is now ready to make predictions on whether customers will churn. In this section, our focus is on building the model, so seeing this message signals we can move forward to evaluate its performance. Run this again if you change your data or try different settings. Let us measure how well our model predicts churn. We use the score method on our test data to check our model's accuracy. Higher accuracy means more correct predictions. We print the result with 3 decimal places for clarity. Running the cell now. The output shows the random forest model achieved an accuracy of about 79.7% on the test data, meaning it correctly predicted customer churn nearly 8 out of 10 times. This score reflects how well the model generalizes to new data, which is crucial for reliable churn prediction in real-world scenarios. What does this accuracy tell you? Would it be enough for a real-world company? Part 6: Clustering and Visualization. For our next analysis, let us try clustering on the mall customers dataset. Clustering finds natural groups in data, even without labels. Running the cell now. Let us load the customer data from a mall for our clustering example. This comment explains that we're setting up data using the mall customers dataset. We import the pandas library, which is useful for data manipulation and analysis. We define the URL where the mall customers dataset CSV file is located online. We load the dataset from the URL into a pandas data frame named mall. We print the shape of the data frame to see the number of rows and columns. We print the first 3 rows of the data frame to get a quick look at the data. Running the cell now. Here, the output confirms we have 200 customer records with 5 columns, including key features like age, annual income, and spending score. This initial data overview sets the foundation for clustering, as these numerical attributes will help us identify natural customer groups. Noticing the variety in spending score and income hints at distinct segments ready to be discovered. Now, we will group mall customers by similar income and spending patterns. This comment describes that we are performing k-means clustering using 2 features, annual income and spending score. We import the k-means class from scikit-learn to perform clustering. We import matplotlib's pyplot module to create plots for visualization. We select the columns and annual income, $, and spending score, 1 to 100, from the dataset as the features for clustering. We create a k-means object to find for clusters, setting a random state for reproducibility. We fit the k-means model to our selected features and predict the cluster each data point belongs to. We add the predicted cluster labels as a new column called cluster in our data. We create a scatter plot of annual income versus spending score, coloring points by their cluster labels. We label the x-axis of the plot as an annual income, $. We label the y-axis of the plot as spending score, 1 to 100. We add a title to the plot to indicate it shows clusters of mall customers. We display the plot on the screen. Running the cell now. This scatter plot shows for distinct customer clusters based on annual income and spending score, revealing natural groupings in the data. Notice how different colors correspond to separate clusters, helping us visually interpret purchasing behaviors without prior labels, exactly the goal of clustering in this analysis. How might a business use these clusters to change advertising or offers? Part 7: Advanced Topics, Ensemble and Anomaly Detection. Ensembles combine several models to boost accuracy. Anomaly detection helps find fraud or rare events. Running the cell now. Let us see what rare events look like in credit card data. This section is about anomaly detection using the credit card fraud dataset. We import the pandas library for data manipulation. We define the URL where the credit card fraud dataset CSV file is located. We read the CSV file from the URL into a pandas data frame named df_fraud. We print the shape of the data frame to see the number of rows and columns. We print the count of each class in the class column to understand the distribution of normal and fraudulent transactions. Running the cell now. This output shows the credit card fraud dataset has 284,807 transactions with 31 features each, highlighting its large size for anomaly detection. Notice the extreme class imbalance, only 492 fraudulent cases, class equals 1, versus 284,315 legitimate ones, class equals 0, emphasizing the challenge of detecting rare fraud events. This sets the stage for using ensemble methods and anomaly detection techniques to effectively identify these rare but critical fraud cases. Why is class imbalance important for fraud detection? Let us use isolation forest to spot potential fraud, even with no labels. This comment explains that we're using isolation forest for quick anomaly detection. We import the isolation forest model from scikit-learn's ensemble module. We select all features except the class column and sample 10,000 rows to reduce memory usage. We create an isolation forest model with a specified contamination rate and random state for reproducibility. We fit the model on the features and predict anomalies in the data. We print out the number of data points the model identified as anomalies, where prediction equals -1. Running the cell now. This output shows the isolation forest model identifying 50 anomalies within a 10,000 sample subset, reflecting the specified 0.5% contamination rate. Notice how the number of predicted anomalies aligns with the expected rare events, illustrating how ensemble-based anomaly detection effectively isolates suspicious data points for further investigation. Try changing contamination to see how it affects the number of outliers. Part 8. Time Series Basics. Time series data helps us spot trends over time, useful for business and forecasting. Here is a tiny example with made-up data just to show the idea. Running the cell now. Let us make up a tiny time series to learn about plotting trends. This is a comment describing this as a tiny time series example. We import the pandas library for data manipulation. We import matplotlib's pyplot module for plotting graphs. We create a pandas series with the given customer counts. We set the index of the series to be monthly date starting from January 31st, 2023. We plot the time series data with circular markers on each data point. We set the title of the plot to describe what it shows. We label the y-axis to indicate it represents customer counts. We display the plot on the screen. Running the cell now. This line plot shows a clear upward trend in customer count over 7 consecutive months, starting from 230 and rising to 300. Notice the time-based index on the x-axis, which is key to analyzing changes over time in time series data. This simple example demonstrates how time series plots help visualize trends critical for forecasting and business decisions. Try changing the numbers to see the effect on the plot. Part 9, Mini Project, Create Your Own Churn Predictor. Let us put it all together. Build a model to predict which customers might leave. Try it on a small sample from the Telecom data. Running the cell now. You will enter values for a pretend customer. The model will predict if the customer will leave. This is a comment prompting the user to enter a sample customer's features for prediction. Print a message asking the user to enter customer features separated by commas with column information. Read the user input as a single string. Convert the input string into a list of integers by splitting on commas and stripping white space. Use the trained random forest model to predict the churn status for the input features. Print predicted churn if the prediction is 1, otherwise print predicted stay. Running the cell now. Here, the code prompts you to input a new customer's data as a list of feature values, which the model then uses to predict if that customer will churn or stay. The output predicted stay indicates the model assessed the provided input as a customer likely to remain, demonstrating how the prediction pipeline applies the trained model to individual cases. This step shows the practical use of your churn predictor in making real-time predictions from raw input features. Practice, try changing the features to see if the prediction changes. And if you are learning, please subscribe to our channel and like the video. Here is a quick challenge. Swap in logistic regression and see if accuracy changes. This is a challenge prompt to try using logistic regression for the churn model. Import the logistic regression class from scikit-learn. Create a logistic regression model with a max iteration limit and fixed random state for reproducibility. Train the logistic regression model on the training data set. Evaluate the trained model's accuracy on the test data. Print out the accuracy of the logistic regression model formatted to 3 decimal places. Running the cell now. This output shows the accuracy of a logistic regression model predicting customer churn, achieving about 81.3% on the test set. Notice how the score reflects the model's ability to correctly classify customers likely to leave, which is the key goal of this mini-project. This demonstrates how changing the model type can impact predictive performance on the Telecom dataset sample. Does this new model do better or worse than before? Part 10. Best Practices and Final Tips. When working with real data, always check your data for quality and missing values. Split into train and test sets. Try multiple models and compare. Tune hyperparameters for even better results. Lastly, practice, experiment, and keep learning. Running the cell now. Congratulations! You completed the data mining capstone. Share your progress and questions in the comments. For more tutorials, subscribe and hit the notification bell. Good luck and keep exploring data. Running the cell now.